Okay, class, today our focus is going to be on scientific notation, specifically using scientific notation to determine the value's significance, also with the bonus section on accuracy and precision. So, first things first, standard scientific notation consists of two factors, and you should know this. The first factor is a number between 1 and 10. So anything greater than 1, or I guess equal to 1, as long as it's like 1.0 or 1.00 or 1.0000000, but the first factor has to be some number between 1 and 10, so that means 9.9999999, but not 10 because then we get two digits, and the goal is factor 1 should always have just one number before the decimal point. Factor 2 then is going to be the power of 10. So keeping things consistent here, factor 1 is a factor that can have as many decimal places as needed. The factor can be positive or negative, so you could have negative 3.47 or positive 8.299. And here's some examples: 4.222, negative 9.3167, or 1.0. Now, factor 2, which is the power of 10, is simply a power of 10. And it will be shown as 10 to an exponent, which can be any integer. So integers are any of the counting numbers, like negative 1, negative 2, or 0, or 1, or 2. It's not a decimal. So examples here would be 10 to the 4th, 10 to the negative 7, or 10 to the 0. Now, 10 to the 0 is kind of rare. You won't see it unless they explicitly tell you, put this in standard scientific notation, and they're trying to trick you. But the reason it's redundant is because anything to the power of 0 is equal to 1, and anything multiplied by 1 is just whatever that first number was. So 10 to the 0, which equals 1, is kind of a redundant factor. Now, so what? Who cares? What about significance? So factor 1 limits the significance. All of the value's significance comes from factor 1, whereas factor 2, which is the power of 10, has no bearing on the significance because a power of 10 is an exact number. So really it's infinitely significant. If we say 10 to the second, we really mean 100.0000000000000 and so forth, right? So because factor 2 is infinitely significant, if you remember, significance is determined by the least significant factor, which will always, always, always be factor 1. Now, here's some examples. 4.93 times 10 to the third has how many significant figures? Well, if you counted the ones on the left, you'll see 4, 9, and 3, so therefore the answer should be 3. How about 7.000 times 10 to the second? It has 4, the 7 and all 3 zeros. Number 3, negative 8.4193 times 10 to the 14th has how many significant figures? Hopefully you answered 5. How about number 4? 6 times 10 to the negative 24 has how many significant figures? There is only one of them. And lastly, number 5, 2.229 times 10 to the negative 8 has how many significant figures? There are 4. The 2, 2, 2, and 9. That was pretty easy, right? And that's kind of why I said, if you always convert to standard scientific notation, you will always, always, always be able to figure out how many significant figures you have, because whatever that factor number 1 is, just count the digits there, and you will have the number of significant figures that you have. But that's not all. Sometimes you need to write a number that can only be significant to a few digits, but you are limited by zeros getting in the way. For example, what if you had to write the number like 4,000 and you needed 3 sig figs in your answer? Well, when you look at 4,000 without a decimal point, how many sig figs does it have? Hopefully you said 1, just the 4, because those zeros, you don't know what that is. And if you wrote that in scientific notation, it's actually 4 times 10 to the third. So, like I said, you should recognize by now that 4,000 by itself has only one significant figure. But if you need 3 of them, the only way you could write that is with scientific notation. And how would you do that? Just like this. 4.00 times 10 to the third. Now you have 4,000, and it's written properly identified as having 3 significant figures. Now, accuracy and precision. You've probably heard this several times. You may have even had a discussion on this in other classes, maybe even with me in a previous class, I'm not sure, but just in case, we are going to go over the difference between accuracy and precision. Accuracy is how close you are to the actual number. So it's determined by how many significant figures are in the value. So let's say, okay, let's say you are pretending that 1 foot, or not pretending, let's say you're estimating that your foot actually equals 1 foot in length, and if you count off 9 of your feet, you would have 9 feet, right? Now, if you also measured it with a ruler, which is a little bit more accurate than your foot, you would find that maybe you have a little bit more than 9 feet, or maybe you have a little bit less than 9 feet, and your accuracy is limited by the type of device that you're using there. But the point is how many sig figs you can actually have in your answer is going to be your accuracy. Now, on the other hand, let's look at precision. Precision is how close in agreement the values are in a measurement. So let's say you are tasked with measuring the room temperature, and there's 5 temperatures, and you get 72, 73, 73, 72, 73, and that's pretty consistent. Consistency and precision they go hand in hand. Now, on the other hand, what if you got 72, 64, 104, 19, and -4? That would be very imprecise. So maybe it's easier if I just show you a picture, and I stole this picture off of this website. I gave you the link down below, but this picture here does a good job of explaining the difference between accuracy and precision and what they mean. And what it shows in picture 1, you'll see there's no accuracy, there's no precision really. But in picture 2, you see how all of the darts are close together, even though they're not near the target, so they're not calibrated, so to speak. They're not close to the target, they're not accurate, but they are precise because they're very repeatable. Now, the next one shows high accuracy, not so much precision. Well, it's high accuracy because they're all in the bullseye, but you can see they're all on the rim of the bullseye. They're not that close to the center, whereas on the 4th picture, where you have high accuracy and high precision, that's where all of the darts are hitting the exact dead center of that target. So that's a pretty good visual to explain the difference, and if you need to pause to look at that, I highly encourage it so that you know the difference between when I say you need to be accurate or you need to be precise, or both. Now, how is that relevant to significant figures? Well, we already said that accuracy is the number of significant figures that the value has. Precision, on the other hand, we'll say accuracy. So if we take 4.90 meters, we can say that 4.90 meters is accurate to 3 significant figures, because the 4, the 9, and the 0 are all significant. Precision, on the other hand, is the location of the rightmost sig fig. In that previous example there, 4.90 meters, that 0 is the last significant figure, and therefore, because it's in the 100th place, we can say 4.90 meters is precise to the nearest 100th of a meter. So last, in summary, when in doubt over the significance of a number, convert it to standard scientific notation. The first factor will determine how many sig figs you have. Sometimes, scientific notation is the only way to display the significance of a number. And since measurements are always prone to some degree of uncertainty, it is important that we pay attention to significant figures in our calculations so that our answers actually mean something besides a jumble of numbers. The number of significant figures in a value will determine that value's accuracy, while the rightmost digit will determine that value's precision.